The objective today is to explain the benefits of using hexadecimal numbers to represent long strings of bits. Now I want you to use the widget to complete a task, so you'll be going to this link right here. When you get there, you can immediately press X on the video and just start experimenting with the 6-bit color by filling in the bottom row of the image with different shades of color. So just like I said, experiment with the numbers.
In this version of the widget, we've made setting the metadata of the image a bit easier. For the width and height, you can type the decimal numbers you want, use the sliders, or type the binary as you did before. It's useful to be able to change these things quickly to see the effects on the image. Notice when you change the data by typing or using sliders, the binary data changes and the image canvas reflects the changes. There's another piece of metadata here called bits per pixel, which will allow us to make more than purely black and white images as we did before. To see what it does, let's set bits per pixel to 1, which is what we had for black and white images before, and let's paste in a familiar black and white image. In order for a pixel to have a range of colors, it seems logical that we will need several, or many bits to represent the color of each pixel. The bits per pixel setting in the metadata tells the widget how many bits it should use to calculate the color of a pixel. You can see if I change the bits per pixel setting, the widget will interpret the bits differently, and you'll see some colors start to appear. Of course, the binary data for this image was written for a black and white image with 1 bit per pixel. But if we change how that data is interpreted by increasing the bits per pixel that the widget is expecting to see, the image gets garbled. Let's start over and try to get the hang of using color in digital images. I'm going to make a very small image so that we can really look at what's happening with the pixels. So I'm going to set the width to 4 and height to 2. Now let's look at how RGB colors work with this tool. As you know, for color images, each pixel is actually a combination of red, green, and blue light. If we want to represent that in binary, the least we can do is allocate 3 bits for each pixel, 1 bit each for the red, green, and blue values. I can use the slider to set the number of bits per pixel I want to use to render the image. So I'm going to set the bits per pixel to 3. So now, with 3 bits per pixel set, it means I can control the amount of red, green, and blue light that goes into each pixel. As before, if I turn all the lights off, I will get the color black. And if I turn all the lights on, I get white. Since I have 1 bit of control for each of the red, green, or blue lights, I can turn them on and off individually. So if I want a red pixel, I can turn on the red light and turn the green and blue lights off. So that's red on, green off, and blue off. 1, 0, 0. And presto, I get a red pixel. Now you keep going and create a green and a blue pixel. Notice that when we have 3 bits per pixel, the first bit controls the red light, the second controls the green light, and the third controls the blue light. R, G, B. Now it gets interesting. What happens if we mix the lights? Let's see what happens if we turn on the red light and blue light and leave the green light off on the same pixel. Before I type it, make a mental prediction. What color do you think we'll get if we mix red and blue? Think about it for a second. All right, ready? Here we go. Red on, green off, blue on. It made pink! Is that what you were predicting? I'm guessing that you thought we might get purple. Well, this is one of the key differences between mixing light and mixing paint. It's actually the opposite physical process. When you mix a lot of paint together, the color gets darker and darker. When you mix a lot of light together, the color gets brighter and brighter. It can take some getting used to, but you'll get the hang of it. With only 3 bits, we know that I can only combine them 8 different ways. So with 3 bits, only 8 colors are possible. Now you keep going and finish the remaining 2 colors.
It'll look something like this. You might do some different colors and see what happens. Look at that, somehow we got red somewhere. So just experimenting. And then the second part, though, is a little more complicated. You'll probably need to jump back and forth between tabs, but here's the directions. It says, we start you out with the 4x4 image Maddie created in the video. Your task is to fill a 4x4 grid with colors using 12 bits per pixel. So that's step 1. Let's make a 4x4 grid. So image width 4, height 4, okay, and then 12 pixels, or 12 bits per pixel, sorry. The next step, here are the requirements. Row 1, fill with shades of red. Row 2 is green. Row 3 is blue. And row 4, shades of gray. So that's the challenge here, to figure out how to do that. And as long as you remember that hexadecimal is just a better way to look at binary, as long as you remember that fact, you'll be okay to use it. So before we begin, we need to talk. Hexadecimal representation is not a form of compression. So I just told you, if you're feeling comfortable with hexadecimal, go ahead and use it. But what I don't want you to do is think that you're compressing binary by using it. All you're doing is visually changing the binary so your brain can understand it so much better, okay? It says here that the underlining binary representation is not changing at all. Rather, it is a more convenient way of representing that binary information. So moving on here, there are 2 more tasks after the third one. Don't spend too much time on them, but enjoy. We have one more informational slide after this one, and then a fun project. That should take you about 15 minutes to complete. Then the DOL, of course, and that should take about 5 minutes. Thinking about images in pixels is a really good way to approach computing in the beginning. These things that were, when I was a kid, very popular. I often use the Doom guy as my favicon, so yeah, I'm not original, I am not very artistic. This project I'm having you do right now, I wouldn't really even know where to begin, but here are some directions. Step 1, you're creating a personal 16 by 16 favicon and encode it using the pixelation widget, so you're familiar with that. You've experimented a little bit with it, so this is the tool we'll use. You must encode with 12 bits per pixel, so this is a color thing. The image you make should represent your personality in some distinctive way. I just told you for my personality I would have done the Doom guy as my favicon, and I think that's very distinctive, and there's a whole backstory as to why I like that game so much. But in the meantime here, just remember that this thing you're creating, it's supposed to represent your personality. And here's an optional part. After you've finished your favicon, share it with others in the class by sending them the bits with the Internet Simulator widget. So here we are on that 15-minute project I wanted us to do today in class. It's creating a favicon. A favicon is a small image, usually 16 by 16 pixels, that is typically shown in a web browser's address bar next to the title of the page or web address for a particular site. It is typically a small version of a company logo or some other symbol for the site. Favicons are designed by artists and programmed into web pages by web designers. So my think right share for you on here is, do you have a favorite company logo? For me, I have to say, anytime I see that strange green mermaid, I just start thirsting for Starbucks coffee. And I drink it black, by the way. I know the holidays are coming up, so if you're considering extra credit, I'm just kidding. So here we are at the DOL. I hope you've spent at least 15 minutes on creating your favicon there, and I'm very excited to see those. So as we're going through class today, raise your hand when you finish so I could check that out. I'd love for you to copy that image or do a screen save with it and post it on Canvas. That would be, how about extra credit for that? So here's the DOL. Why are hexadecimal numbers better to use when working with long strings of bits?